Today's webinar will focus on the Water Network Tool for Resilience, WNTR. This tool can help water utilities investigate the resilience of their water systems to a wide range of hazardous scenarios and evaluate emergency response actions and long-term resilience enhancing strategies. If you have a question during or after the presentation, we ask you to please type it into the Q&A pod at any time. And once the presentation ends, we will answer as many questions as time allows. We encourage you to listen through your computer speakers. And we will make these slides available on our EPA research website within the week. I'm sure that Erin has typed that in or will type in that web address for you. Our presenter today is Terra Haxton, and before she begins, I'm going to turn it over to Dr. Sean Ryan. Sean is our National Program Director for EPA ORD's Homeland Security Research Program, and he is going to briefly introduce the topic and then our speaker. Thank you.
Thank you, Lisa. Can you hear me okay?
Yes, good.
All right. So thank you. So as Lisa mentioned, I'm the director of our Homeland Security Research Program within EPA's Office of Research and Development. And our research program really seeks to advance EPA's capabilities and those of our state, tribal, and local partners to respond to and recover from contamination incidents and improve our ability of water utilities to prevent, prepare for, respond to, recover from water contamination incidents that might threaten public health. So in the program, in the Homeland Security Research Program, we perform applied research that delivers relevant and timely methods, tools, data, technologies, technical expertise, whatever's needed in support of our federal, regional, state, tribal water systems and local communities to ensure resilience or build resilience. And so today I'm really excited to introduce Dr. Terra Haxton to present a tool that EPA has developed to support water utility resilience. It's called the Water Network Tool for Resilience, or for short, WNTR. Dr. Haxton is an engineer in EPA's Office of Research and Development, Center for Environmental Solutions and Emergency Response. Since joining EPA in 2007, Terra has helped develop water system modeling approaches to assist drinking water utilities in improving security and improving resilience to natural disasters. She holds a BS in civil engineering and an MS and PhD in environmental engineering from Vanderbilt University. Dr. Haxton, turning to you.
Great, thanks, Sean. Sound check, please.
I can hear you. Yep.
Great, thanks. Well, thank you all for joining us today. I really appreciate your time in attendance. I'm going to go and tell you a little bit about the Water Network Tool for Resiliency. So a little bit of background and motivation for our research area is that there is more than 50,000 community water systems around the United States that supply high-quality drinking water to customers. However, these systems can face a variety of challenges, such as solving water quality problems, such as customer complaints or local or individual, replacing aging infrastructures that might occur, such as leaks or broken pipes or inoperable valves. They also have to look at optimizing operations in terms of what is the best time to operate system components in terms of energy usage. They also need to manage emergencies that might happen in terms of disasters that might befall them, as well as planning for the future in terms of building resiliency into their system. So some of the natural potential hazards that a water utility might encounter are listed here in this table on the right. There are natural disasters such as earthquakes, floods, hurricanes, or wildfires, as we're seeing very recently in the news. There also could be the potential for terrorist attacks, cyber attacks, or just in general hazardous materials that we release that might become into the system, such as the Elk River release that was, or the release that happened in Elk River in West Virginia. And these different hazards might have different potential impacts on the distribution system in terms of infrastructure damage, such as pipe breaks, pump failures, or tank damages. They also could be service disruptions, There could be changes in pressures or water quality, as well as societal and financial impacts. So our goal is to help these drinking water systems build resiliency to all kinds of disasters. And so the goal of a resilient system is to minimize the magnitude of the disruption as well as the duration of that disruption. So the resiliency of a drinking water system is influenced by the design as well as the maintenance and operations of those systems. And it can also be influenced by the dependency with other critical infrastructures such as electrical. So in the figure in the right, we are highlighting a measure of the resiliency in terms of different performance metrics. This could be the number of customers impacted or number of maybe the cost of the impact across time. And so if there's some kind of original state that this utility is operating in, and then some kind of event, say like a hurricane or something that happens and disrupts the system, and this is the magnitude of the disruption, and then it occurs along some timeline, and then they are able to gradually get back to their recovered state. But however, if they are able to build resilience in their system, then the magnitude of the incident is much less, as well as the duration, and they're able to respond and remediate the system much quicker. So that is our goal of the resilient system. While there are general water sector resiliency guidance available, and I've highlighted a few here, such as the SIPAC report that here, and if you click on this different images in this slide, you're able to actually link to these systems, and then you can learn more about them there. So the Office of Water also has some general resiliency guidance as how to repair and maybe respond to these events. And so I've highlighted a few here in terms of the drought, earthquake, power, and floods, and these are available again if you click on the image. And then also there is the American Water Works Association's Risk and Resiliency Management of Water and Wastewater Systems, the J100, that offers kind of assessment of how the utilities might be able to respond. However, we want to be able to do more site-specific analysis. So recently there have been some infrastructure resiliency policies that have been passed. In 2017, the Army passed a directive called Installation, Energy, and Water Security Policy. And this was established so that energy and water infrastructure requirements that ensure continuous availability, reliability, and quality of these systems. And they need to be able to prepare for extended outages, providing the necessary energy and water for a minimum of 14 days. In addition to the Army, there are other similar directives that the Department of Defense has instigated at other military installations. In 2018, there was an update to the Bioterrorism Act called the America's Water Infrastructure Act that required drinking water systems serving more than 3,300 people to develop comprehensive water system risk and resiliency assessments and emergency response plans that address physical and cybersecurity threats. This act built upon the Bioterrorism Act, which including assessing the risk of contamination incidents to include different disasters from all kinds of hazards. To help with this risk and resiliency assessments, the utilities might be asking a variety of questions. They might be interested in what type of infrastructure damage could be caused by specific disasters, such as a hurricane, and what kind of damage might be occurred with that. How long can a system continue to provide customer with the water that they have requested? How many people would be impacted by the specific disaster? What is the best response in the immediate aftermath in terms of getting the service back online to as many customers as possible? As well as which components could they be targeted in the future to minimize these disruptions if they were to occur again? And so in the lower figures or pictures, I just highlighted some of the major disasters that might occur to drinking water utility, such as an earthquake and a landslide that might have happened, pipe breaks that occur quite frequently that cause a lot of flooding and damages, as well as winter storms. So while the general guidance is available, we feel that a site-specific analysis using hydraulic models might be the way to allow a water utility to dive deeper into their understanding of how the system might actually function and operate during emergency conditions. So you're able to use water distribution system modeling tools to help you quantify the consequences of different disasters, and then evaluate and prioritize resiliency enhancement actions that might be beneficial. Using those information, then they're able to justify the capital investments in building resiliency. So using hydraulic modeling is an approach that is a system-based approach to solving the problems rather than looking at individual components. So using a distribution system network model, you take into account the physical infrastructure such as the pipes, tanks, pumps, valves, etc. that might be in there, as well as the customers that are reflected in the customer usage demand of how much each customer is consuming water, in terms of the governments, in terms of how they operate the system, in terms of turning on different pumps and tanks at different times to minimize the energy consumption, as well as services in terms of the amount of water that is produced and consumed. Using all this information together, then you're able to create a hydraulic network model that is then used in modeling and simulation tools such as EPANET or other commercial entities. And using those, you can simulate the flow, pressure, and water distribution system quality in the distribution system itself. That is depicted here in the little diagram. This is what a distribution system network model would look in EPANET. You can highlight different characteristics of the model, such as the red here is highlighting different diameters of pipes. So I'm going to give a little bit more background on the distribution system network modeling itself, and for those who are unfamiliar. So with the distribution system network models, you're able to represent the actual infrastructure. So you're able to say that how many gallons of water per day that are supplied to the system, as well as the number of customers that may be served. You're also representing the sources of the water, such as if there's multiple reservoirs. And in addition to that, you might have to represent the pumps, tanks, and miles of pipes. In the image depicted on the right, you can see here the distribution system network model, and we're highlighting the elevations of different locations in the model through different colors of feet, and then as well as the diameters of different pipes. You see the larger pipes are more transmission lines that are coming directly from the treatment plant. In the distribution system network model, you're also able to represent the customer usage. And so this is able to represent the number of customers that is being served by the distribution system network, as well as the different patterns of consumption. Excuse me. So there's 3 examples here. We have a residential use, a commercial use, and accounting for unaccounted water, which might be non-revenue water. So here on the right, again, we have some depictions of the patterns that might be associated with a different customer usage. So here we can see this is a residential use, because the pattern is much higher, say much higher demand during the day and the evening versus the middle of the day, which obviously this is pre-COVID, where most people were leaving their house to go work. And then here's another, this is a pattern that was associated with the commercial use. So again, it's a higher demand use during the middle of the day when people are at their offices or buildings. And then the final pattern is the unaccounted for water, and it's just a flat pattern that could be applied across the network to account for non-revenue water or other unaccounted for water. So in addition to these other things, we were able to represent the operations of the distribution system network model. And in this category, we're able to look at how the system is actually turning on and off different pumps to fill the tanks. So for example, in this, we're looking at the pump is turned on if that tank is below 5 feet, and turned off if the tank is above 19 feet. And you're able to see and represent the dynamics of the system. So in this graph here that you can see over time, you can see how the head or the volume of the tank fluctuates over time. And you can represent that basically from the data that you're collecting from the system in the actual network model itself. Using all this information in the distribution system network model, then you're able to simulate the different conditions in the system for the hydraulic and water quality. So here is some depictions of the hydraulic conditions that you can represent and predict. So in the left figure, we're looking at the pressures in the system. And the pressures range from less than 25 pounds per square inch, or PSI, to greater than 100 PSI. And you can see that this might be useful for our utilities, maybe to identify areas that might have low pressure conditions that they might want to help and maybe increase customer demand in that area. Because I know that there are some regulations associated with low pressure that might be of interest to some utilities. On the right is a depiction of the flow in the system. And here we have highlighted that the flow can range from less than 25 gallons per minute to greater than 100 gallons per minute. The thicker red lines will probably represent more transmission lines that are flowing directly from the treatment plant to maybe the high service areas of the distribution system. So the utility can look at different characteristics like that to see if maybe if something were to happen to those pipes, they might be of greater concern. In addition to the hydraulic conditions, you're able to predict the water quality. One water quality metric that is commonly used is the water age, which can be a surrogate for declining water quality conditions or low chlorine residual. So in this map, we're looking at the water age ranging from less than 24 hours to greater than 96 hours. And as we can see from the treatment plant, it's probably up this way, and so it has, as it flows from the treatment plant to different locations, as how the age increases. So the blue one is much closer to the treatment plant versus other locations. Here you can see that the tanks are all red, and usually that is because they are just don't get circulated as much, and so therefore the water age just increases. Water utility can use this kind of information to identify maybe locations that might be low on chlorine residual, and maybe decide that they might need to have chlorine booster pump stations installed. So once the water utility has a water distribution system network file and can do these different simulations, we can use a tool like a water network tool for resiliency, WNTR for short. And this is based on the EPA's tool EPANET, which is used a hydraulic and water quality simulating engine. It adds additional capabilities on top of what EPANET already offers. So WNTR is designed to analyze water distribution system failures and recovery options. So the input to WNTR involves a variety of different things, as I highlighted in this figure. So it includes the water distribution system network model that I've previously described to you, as well as the hydraulic and water quality simulations. So for the simulations, we can look at where water may be flowing from one location to another. We also want to look at disaster models, and this might be taking into account where earthquake might occur or where it might be potential for landslides. In addition to that, you want to look at probability of damage. And so for these two together, you can kind of look at different pipe ages. Maybe there are different distributions of pipes that have been installed, and maybe some are more prevalent to pipe breaks than others based on age. You can use that information as an input to WNTR. You can also use information related to the pipe material. So here we kind of depicted that there are 3 different pipe materials in this distribution network, whereas black is cast iron, the aqua green color is ductile cast iron, and the reddish color is polyurethane. And so you're able to highlight this and use that information maybe if you're doing such as the earthquake analysis, then you can say that these pipes are more susceptible to breaking due to that damage. And this figure here, we're able to look at probability of damage. So maybe there is some kind of like peak ground acceleration from an earthquake and related to what is the probability of that pipe maybe breaking or tank. So here you have an orange, an area that is a probability of major damage. Blue is minor damage, and white is no damage. So you can look at different characteristics of this and incorporate that into your analysis. Another component that WNTR is able to do is look at the response and mitigation actions. And you're able to look at these in terms of the, as well as the resiliency consequences analysis assessment. And you can look at these in different terms. And so in this figure here, or this plot, we're looking at population impacted over time. And as we're doing different repairs of the tanks, pumps, and pipes, you can see that we're able to decrease the population that's impacted. So you can look at these different characteristics of the system and different measures. For more information about where to download and install WNTR, you can click on this link here. So a little bit more background on the WNTR framework. It is an open source Python package that is freely available to download and use and modify as necessary. It integrates commonly used and efficient Python packages that are also open source and freely available, such as that enables the display of graphics and numerical analysis packages that are available as well. If you click on this image here, this is the online documentation and user manual for Winter itself, and so it's able to give you a little bit more background of the tool. The code itself in Winter is available through a GitHub repository, so every time that we make changes to the code, it is documented and everybody can see what is made changed and so forth. And as every change is made, we're able to test that to make sure that the changes did not actually break the system or the tool and make it make erroneous results. These pictures are kind of just a depiction of how you would use Winter and the spider framework. And these are some of the graphical depictions that you can see. This is just a picture of the pressure at hour 5 in the simulation. Again, it's very similar to the previous graphs that I've shown. Other graphical representation of the data can be like on a GIS type layer map. And here you can see that we kind of overlaid the pipe network, and you can click on different features of this to highlight what the pressure or the elevations and the diameters and the lengths of these different pipes are. So now a little bit more background on the Winter Water Network model components. So within Winter, you're able to generate network models from EPANET IMP files, or these are the input files for EPANET, or you can directly create them from scratch, maybe from GIS layers or other data sources that the water utility might have on hand. You're able to model the model contains the physical layout of the system as well as system operations, as I previously mentioned, in terms of operations of the tanks and pumps. You're able to add and remove and modify the components. So if you're looking at different scenarios that you want to say maybe what happens if you took out this tank, how the system operates, you can remove the tank. Or if you maybe want to add a tank to see what the effects of maybe adding more storage into your system and how it would be more resilient or redundant in that case. Within Winter, you're able to query the attributes of the different components, and so you can look at maybe what are the pressure conditions at different locations or the actual flows in certain pipes themselves. You are also able to skillsize the system. So I've depicted that here. So most water utilities are going to a distribution system network files that represent all of the pipes in their system, but sometimes that might not be necessary to actually use all of those pipes in analysis. And so maybe you only want to do analysis that has a 12 inches or greater analysis. That's kind of where you can scale science in the network model. And this allows you to do a little bit more efficient simulations. Again, as I mentioned previously, you can highlight different and assign different characteristics to different features. So here we assign different pipe materials to different pipes and color code them accordingly. Another feature within Winter is the ability to analyze the network structure, and this allows you to see how interconnected different components are, and you can see how redundant the system is, and these are built-in features. Winter is also has the hydraulic and water quality simulations similar to EPANET. So it has the demand-driven hydraulic simulation, which was the standard practice up until a few years ago, where the demand is whatever the customer wanted they would get, even though that might not have been realistic based on the pressures available in the system. A new feature is the pressure-dependent demand hydraulic simulation, and this is looking at demands that are received in a node that are dependent on the pressure available at that location. So here in the graphic here, we're looking at the demand that is available versus the pressure. And so if it's above a certain threshold, PF, then the customer would get all the demand that they would actually want, or all the water they wanted to consume. If it was between pressure of P0 and PF, then they would receive some percentage as given by this equation of their actual customer usage and demand that they wanted. If it was below PO, then they would not receive any demand at all. And this is more accurate representation of how the distribution system works in reality. Winter is also able to, as I said, simulate the water quality in systems in terms of water age or contaminant concentration. Winter also has the ability to start and stop a simulation. So if you want to simulate maybe a pipe break or something like that, you're able to stop a simulation, change the characteristics of the model, and then restart it without having to do the whole simulation again. Winter also allows the ability to do Monte Carlo simulations for sensitivity analysis and other things, so that you can see how the variety of different parameter combinations impact the overall characteristics, so you can get like a median response as well as the ranges. In a winter analysis, you're also able to parallelize the simulations, which means that you're able to run multiple simulations at one time, which is if you're running a lot of simulations in terms of the Monte Carlo simulations, then you're able to spread this out over multiple computers to allow it to be more efficient. As I mentioned, Winter has the ability to model disruptive incidents. So you can define this incident based on data or a specific model. So here I have some examples of the type of information that can be supplied to Winter. This is a peak ground acceleration map that can be supplied by the USGS shake maps and so forth, and tells you like where the location of the epicenter would be and how what the peak ground accelerations would be about that. And you can use that information as an input to the Winter analysis. You can also get and use maybe 100-year flood map stages, such as this one depicted in Virginia, as inputs to know that maybe some of your pipes might be in flood zones. Winter also has the ability to directly model an earthquake scenario built in without having to use the USGS information. Within Winter, you're also going to define the probability of failure with these fragility curves that I previously mentioned. So again, this is a probability of some damage occurring against an environmental change, such as a peak ground acceleration. And the purple-orange is, the orange-brown is the major probability of major damage. The blue-navy is the probability of minor damage. And again, the white is the probability of no damage. So you're going to supply this information and lay it over the distribution system network map as depicted here on the right. So again, the orange-brown colors of these areas that might affect have major damage, whereas the blue system, the other part of the system, is receiving minor damage. Within Winter, you're able to modify the model itself by changing the controls of how you operate the system, and maybe changing the demands. Maybe you want to look at a situation where you maybe the demands are increasing because of the incident, or maybe they decrease, so you can change what the consumption rates are. And you also can look at different components to each scenario, so you're able to modify this as necessary. Winter also includes the ability to model restoration actions. So you're able to define maybe the number of types of repair actions that you're interested in, number of crews that might be helping you do the repair, and the time to repair. And again, this is an example of a repair strategy that we found from the 2014 Napa Valley earthquake. So they had a number of repair crews as 5, and each of those repair crews were able to do about 5 repairs per day. And the repairs started about 24 hours after the earthquake, and then they had separate teams to repair the pipes versus the tanks. And then they prioritized the proximity of the traveling to different locations by the time, and so that they're able to like maximize the leaks and so forth. We're able to define the priorities and distance from the reservoir or the maintenance yard in terms of like maybe it's faster to get to some locations versus others. Maybe you can define different priorities in terms of the magnitude of leak, like this one pipe is leaking a lot versus another one, so you might want to fix the pipes that are broken and have the greatest leak value versus the lower one. You also might want to define a priority in terms of the people affected. Maybe this pipe break is affecting the whole system versus a system that, or a pipe break that maybe only affected, 2 or 3 customers. And again, you're able to take different components and model them and control them and modify them as necessary for the scenario that you're interested in. Finally, using all this information, you're able to quantify resiliency. There are numerous metrics that have been suggested to quantify resiliency, reliability, robustness, redundancy, and security. And so we just have a selection of those available within Winter. We define those as topographic metrics in terms of maybe how connected the network is to each other in terms of redundant pathways. There's also hydrolyte metrics in terms of pressure conditions and flow conditions. There's water quality metrics, maybe in terms of water age or chlorine residual. And again, economic measures related to cost. Some commonly used metrics that we have used in our case study applications include water service availability, which is a metric that defines the amount of water that a customer actually wants versus what they actually receive. We also looked at the population impacted by the disruption, or maybe low pressure conditions. Another common one is water age or chlorine residual, as well as the cost associated with these repairs. And so these, I'm just highlighting a few of the metrics that we have used with our case studies and different ways to graphically represent those. So on this axis, we have the average system pressure over simulation time. The dashed line is the event that happens, and you can see how the pressure changes after that event and actually drops down over time. In this scenario, we were looking at different metrics that are measures that we could use to mitigate that by using different conservation metrics, and we could see how much that conservation metrics allow the pressure to continue for a certain amount of time. This is also looking at another graph looking at the water service availability at a specific hour in the simulation. And so again, this metric ranges from 0 to 1, and this general downtown area is basically the red, so it's not receiving any of the demand that the customers were, versus like maybe the suburbs area are receiving a greater percentage of the water that they had requested. So this is different ways to graphically display this resiliency information to the utility itself. So within Winter, we have a variety of different resiliency analysis options available. So we can look at the hydraulic connectivity during normal and abnormal times of service. So we can look at maybe the flow from the treatment plant and where does it go, where does it service, and so forth, maybe specific tanks. Then we can look at component criticality analysis, which is ranking the individual component failures. And for this, we can look at the effects of different pipe breaks or different pump outages or tank damages and so forth, and what are those individual components? What is the impact of those being out of service? And we're also able to look at overall system resiliency in terms of a specific event. So here we kind of depicted an earthquake event and how it impacts the whole system. I want to go into a little bit more detail about all of these different analysis options available within Winter. So the first is the hydraulic connectivity, and this is kind of where we basically start to just get a better understanding of how the system operates. So we're available to evaluate the critical path between a water treatment plant and its customers. Then we're able to compute the upstream and downstream locations from tanks, valves, or pumps that might be of interest to the drinking water utility itself. So here in these figures, we're able to see that the treatment plant is located here, and it flows downstream with these red dots to the tank that is tank 1. And then tank 1 then feeds and provides water to these locations in blue. This tank serves about 11,000 people. We can then move on to tank 2 and see how it is fed by the treatment plant down these red line paths to the treatment or the tank 2 right here. And then tank 2 is able to then feed these locations highlighted in blue. This gives a little bit more perspective to know that if those tanks were going out of service, who would be impacted. In terms of pipe criticality analysis, this is one that we've recently done with a utility in Region 2 of EPA, and it is located in New York State. This is looking at pipe criticality in terms of pipe breaks greater than 12 inches or more. We were able to identify populations that were impacted by low pressure conditions. We're also extending this analysis to include valve segments, so it lets us know that which segments are valves are critical to maintain as the segment would grow than if a certain valve was not operational. The utility is looking to use this information to help them prioritize capital expenditures so that they know maybe where to put, have redundant supplies on hand. So with this analysis, we're able to, again, plot the results on a GIS layer kind of thing. And this is an HTML file that the utility then can click on and see like, okay, this pipe, if it was broken, the graph's probably really small, but is able to impact people, more than 5,000 people in the network. And so if they click on this pipe, then it expands to this location and shows you that these are all the connections in the distribution system network model that would be impacted if that pipe were to break. So this is valuable information for the utility that maybe they would like to say, hey, we need to have backup supplies to help make sure that that pipe, if it were to break, we would have immediately be able to get back online. And for this analysis, we did different pipe-to-pipe links, break leaks, excuse me, like we looked at pipes broken for 48 hours versus 96 and saw the differences there. In terms of other pipe or criticality analysis, we can look at power outages. And this is looking at power outages to obviously pumps. And we were looking at here an incident where the power was taken away from the pumps, and then it was restored here about 15 hours later. And you can see that the water service availability was the metric again over time. And so we first looked at each individual pump being out of service, and so we started with that we see here is pump station 15. Didn't really, if it was out of service, didn't really impact the water service availability. Whereas if you looked at pump station 3, it had a greater impact. Then we also were able to look at if all four of those pumps were out of service, then we said that all, and we saw how much greater the impact would be to the water service availability. And so here we were just visually highlighting which of these pumps were out of service. So that we were able to do different analysis with which they're using this. So with the same utility, we are also looking at the compromised water source. This is analysis to look at if the river were to be contaminated and they weren't able to pull from the river, or if there was some kind of treatment plant failure, or their intake was frozen, how long would they be able to supply water to their customers? And so we tracked the water pressure and service availability over time, and then we looked and tested different mitigation strategies. So this is average system pressure versus time. And again, this is when the water source loss was happening. And so you can gradually see that the pressures in the system were normal. But after about 10 hours in the system, you can see that the downtown area lost pressure, whereas the suburbs did not. And then a little bit later, you can see gradually as the impacts change over time. And so about 60-some hours later, then the whole system lost pressure. So the system was able to know that how much storage capacity they had over time, and they can look at different components to maybe increase that storage capacity if they had to maybe close their intake due to contamination incidents. The earthquake analysis is also another option. We based this on the 2014 Napa Valley earthquake. Again, we looked at the water service availability and the firefighting capabilities. Assuming that there was a earthquake along this fault line here and epicenter was located there, we were able to use the probability of failure again graph with peak ground acceleration for different components. We're able to look at that in terms of different functions of the soil type, pipe material, and see the impacts of those. We're also able to look at different repair strategies. So we looked at a number of crews, tanks, and pumps that could be repaired by different crew members. And then we prioritized the largest leaks and pumps closest to the reservoir to fix quickly. In this graph, we're looking at the water service availability over time. And you can see that we did a multicolored simulation here. So we saw that there was the black line represents the medium case of all these different simulations. And you can see that it took them about 7 days to recover after this earthquake. And you can see that there's fluctuation over time because of the diurnal patterns of the water consumption. So in addition to those case studies I've highlighted previously, we do have some ongoing case study applications. We are working with Fort Campbell Army Base in Fort Campbell, Kentucky, and they're interested in the general resiliency and pipe criticality, as well as that 14-day water security and energy initiative, where we need to look at alternative water supplies. We're also working with Pittsburgh Water and Sewer Authority in Pittsburgh, Pennsylvania, and they're looking at, again, the general resiliency, pipe criticality, as well as the landslides that might be potential in their area. And we recently started working with the Water and Power Authority in the U.S. Virgin Islands, and the islands of St. Croix, St. Thomas, and St. John. And there they were looking at, in addition to the other general resiliency, they wanted to look at firefighting capabilities, hurricanes, and earthquakes. So we're working with those utilities and hopefully to learn more about our applications with them. So water utilities can use the case study analysis results to help them, again, inform capital and operational investments, whether to maybe invest in additional storage capabilities, or maybe having backup repair supplies for different tanks and pumps. And then we also might want to look at additional repair crews, maybe saying that they, if they had 2 crews versus 3, what would be the benefit of having that? They also can look at maybe locations that they might want to have backup power supplies or generators. So they can use this information to go back maybe to their board and ask for additional investments in their utility. The utility can also use the information from a winter analysis to assist in training exercises for emergencies. You're able to quantify the consequences of different disasters, and then you can compare the different response and mitigation strategies that you might want to implement during these tabletop exercises. In terms of future directions, for winter, we want to be able to incorporate optimization algorithms to help us prioritize response and mitigation actions. We've heard that the Los Angeles Department of Water and Power is looking to identify the order of which they should replace current pipes with earthquake-resistant pipes, so maybe we could look at analysis where we optimize that installation. We also want to extend and expand the capabilities to simulate different disaster scenarios, such as a long-term power outages, such as represented by a black sky event, which is greater than 1 month. We also want to develop an example of disaster scenario scripts that make winter more usable by different groups. And these are maybe just making sample scripts available for pipe criticality analysis, earthquake analysis, or just more of a plug-and-play environment. And as always, we wish to engage with additional case study partners. In summary, we'd like to say that there are a lot of, winter provides a wide range of capabilities to help drinking water utilities do a deeper dive and to understand the resiliency of the drinking water system. We're able to integrate hydraulic models and resiliency metrics to help water utilities quantify the benefit of different response actions and long-term mitigation strategies. This is an open source software that makes these methods available to a wider audience so that anybody can use, and it's free to use. And again, we're always looking and want to encourage other people to work with us on case studies in terms of water utilities, research groups, or other governmental agencies. That is the conclusion of my talk. I would like to acknowledge my colleagues that work on this effort with me, Regan Murray and John Burkhart from the U.S. EPA's Office of Research and Development, as well as my colleagues at Sandia National Labs that has helped us develop this tool, Kate Kleiss, Carl Laird, Michael Blum, David Hart, and Jose Haig. And here's my contact information if you have any more questions, as well as a link to Winter. I'll take any questions at this time. Thank you.